Good evening once again, children. I'm back. I hope you finished the answer to question number 4.
Yes, ma'am.
Yeah. So the question is from a cuboidal solid metallic block. A cuboidal, not cubical, cuboidal. You can see the dimensions. Length 15 centimeters, breadth 10 centimeters, height 5 centimeters. From a cuboidal solid metallic block of dimensions 15 centimeters by 10 centimeters by 5 centimeters, a cylindrical hole, not just a circle, a cylindrical hole, meaning a cylinder, a cylindrical hole of diameter 7 centimeters, diameter, so radius 7 by 2, is drilled out. What will be the height of the cylinder that's drilled out? The diameter is 7 centimeters. What is the height of the
5 centimeters.
From the figure you can make out the height of the cylinder is 5 centimeters. We can make out from the figure that the height of the cylinder will be 5 centimeters. So for the cuboid, you know L, B and H. And for the cylinder, you know the radius is 7 by 2 and the height is 5 centimeters from the figure. It is not given in the question, but from the figure you can make out that the height of the cylinder will be 5 centimeters. All right. So find the surface area of the remaining block. Find the surface area of the remaining block. Tell me the expression in words, children. What will be the surface area of the remaining block?
6s square plus 2 pi rh minus 2 pi r square.
No, again. Come again.
6s square plus 2 pi rh minus 2
Oh
pi
no,
r.
there is no cube here. It's a cuboid, not 6a square.
LBH plus 2 pi rh minus 2 pi r.
Surface area. LBH has no work here. Surface area.
And 2 into LB plus BH plus HM.
Okay.
Plus 2 pi rh minus 2 pi r square.
Plus 2 pi rh minus 2
pi r square.
Okay. Anybody else? The surface area of the remaining block. Well, if you think.
Ma'am, the surface area of the cuboid minus the area of the two circular base, ma'am.
Correct.
Plus the CSA of the cylinder.
Very good. Very good. That's exactly what even Shakti meant. Very good, Parkavi and Shakti. Both of you are right. Okay, so it is the total surface area of the cuboid. Total surface area of the cuboid. Total surface area of the cuboid. But from the total surface area, the area of two circles are missing. The area of one circle on the top and the area of one circle at the bottom, at the base. Because a cylindrical hole is drilled out. So on this top face, the area of the circle is missing because a cylindrical hole is, a cylindrical hole is removed, meaning a cylinder is removed. A cylinder is drilled out. So that means when a cylinder is removed, this one, the circular portion is open. Similarly, on the base, the circular portion is open. There's no material here. So TSA of the cuboid minus, see, where are the two circles? Why are we subtracting from the TSA of the cuboid? Because these two circles are reducing the total surface area of the cuboid. Where are the two circles? On the top face and the bottom face of the cuboid. Because of the absence of the two circles, that is the material there, the total surface area of the cuboid is affected, is reduced. It's affected meaning it's reduced. On the top face, area of one circle is missing. On the bottom face, area of one circle is missing. So the total, so why are we subtracting from the TSA? Because the two circles lie on the top and the bottom face of the cuboid. So TSA of the cuboid minus area of two circles, area of two circles. This is the actual TSA of the cuboid. From the TSA of the cuboid, if you take away the area of two circles, this is the actual net surface area of the cuboid. Plus the CSA of the cylinder. Plus the CSA of the cylinder. Plus the CSA of the cylinder. Children, it's very easy. See, imagine you'll have to paint up this block. You need to paint this block. Where all will you paint? You will paint the TSA of the cuboid minus the area of the two circles. Correct? You can run your paintbrush on all the four surfaces. All the four surfaces. The vertical surfaces. Okay, the vertical four surfaces can be painted fully. Top surface you can paint minus area of one circle. Bottom surface you can paint minus area of one circle. So which means you can paint all the six faces minus the area of two circles. That is what is TSA of the cuboid minus area of two circles. Now imagine you're done painting these portions. Is it over? Inside, if you look inside the cylinder, the CSA of the cylinder is not painted. After painting the four, see you paint this one, the surface. You paint the back surface, the front surface, this one, top and bottom. Okay. You painted the six surfaces minus the area of the two circles. And you think you're done. Imagine that you think you're done, but actually you're not. If you look inside this hole, you will see that the CSA of the cylinder is not painted. If you look into this hole, you will see that the CSA of the cylinder is not painted. Paint that also. When you paint that, the entire of the block is painted. There will be no surface unpainted. See, the question is not about painting, but whenever it is surface area, just imagine you have to paint up the solid with you. So you can paint the TSA of the cuboid less the area of two circles minus the area of the two circles. But if you paint this one, you're not done. The CSA of the cylinder, if you look inside this hole, you will see that the CSA of the cylinder is unpainted. So you'll have to paint that. If you have to add area, if you have to paint that, also add that area. If something is missing, subtract that area. If something is missing, subtract that area. So plus 2 pi RH. See, now why are we taking away the area of the two circles? Because when you find the TSA, it is also this area. When you find the TSA, you're taking the area of this whole face. But actually so this TSA includes the area of the circle and the circle. But they are missing. So since TSA includes these areas, but they are actually missing, you take away those areas. What's the answer? Has anyone completed?
583 centimeters square.
How much?
583 centimeters square.
583 centimeters square. Let me see. 583. Which one? Oh yeah, you're right. Okay. Okay, This is also what I explained now is also correct, children. This is more still in detail. I've taken it up separately. See that CSA of the cuboid. CSA of the cuboid. The curved surface area of the cuboid is intact. The CSA of the cuboid is intact. Okay, so CSA of the cuboid. On the top face, okay, the base, area of the base. In the base, area of one circle is missing. So minus area of one circle. Area of the top minus area of one circle. I've still elaborated here, that's all. What you just understood is also right. This is still elaborate. CSA of the cuboid. This is fully available to be painted. The CSA of the cuboid is fully available to be painted, the four walls. Then base minus area of one circle, top minus area of one circle, plus the CSA of the cylinder. So 2h into L plus B plus LB, because area of the base, length into breadth, minus pi r square. Plus LB minus pi r square, plus 2 pi RH. So I've just simplified this. 2h into L plus B. See, you can find out everything separately and add. You can find this separately, this one, this one, this one, this one separately and add everything. I've done everything together. You can find this separately, this one separately, this one separately, this one separately. So 4 steps and then add the 4 areas. So since you have LB minus pi r square, LB minus pi r square, I've written 2 of LB minus pi r square. 2 times, no? LB minus pi r square, LB minus pi r square. So 2 times LB minus pi r square plus 2 pi RH. Then I'll substitute the values. See, you don't have to do this also. You can substitute after writing this step, you can directly substitute the values. After writing this step, you can also substitute the values. You don't have to write 2 of LB minus pi r square. Not that you must write this. Okay, now substitute the values. 2 into height of the cuboid 5, L plus B 15 plus 10. 2 LB 15 into 10 minus pi r square 22 by 7 into 7 by 2, 7 by 2. Plus 2 pi RH, 2 pi RH. Height of the cylinder we understood is 5. The height of the cuboid 5 centimeters. So children, see, on working this, the surface area of the solid is 583 centimeters square. Please complete it. If you have not completed, please complete it. Done, children?
Yes, ma'am.
Take a screenshot. We need to continue with circles. We need to continue with circles. Please take a screenshot in case you have not written the 5th and 6th question. Take a screenshot and you can complete it as homework. I'll show you the answer slide also. Okay, I hope it's done. The answers to question number 5 and 6. 5 you can see there. You can see 5. 6 is continued in the next page. Take a screenshot.
Yes, ma'am.
Yeah. Okay, this reminds me of something else. Yesterday, Parker, we had a question from this chapter. 1 minute, let's do that now. I'll write the question, or if you take down this question. This question is also from the same chapter, surface areas and volumes. Please write down this question. A conical vessel of radius 12 centimeters, and height 16 centimeters is completely filled with water. Is completely filled with water. I need to clear the question, so please write the question along with me. A conical vessel of radius 12 centimeters and height 16 centimeters is completely filled with water. A sphere is lowered. A sphere is lowered into the water. A sphere is lowered into the water. And its size is such that, when it touches the sides, it is just immersed. It is just immersed. What fraction of the water? What fraction of the water overflows? What fraction of the water overflows? Yes, children, we'll understand this. Please write the question. Done writing? Class finished writing?
Yes.
Okay. So a conical vessel. Imagine a conical vessel of radius 12 centimeters and height 16 centimeters is completely filled with water. So it's filled with water to the brim. So what will happen if you drop a spear? If you drop a spear, then the water will splash out. A spear is lowered. So gently you immerse a spear. A spear is lowered into the water. A spear is, you don't throw a spear into the water, then water will just splash out. A spear is lowered. So gently you lower a spear into the water. Obviously, water will overflow because the spear is going to take up some space. So correspondingly, some water will flow out. Whatever is the volume of the spear, that volume of water will flow out. The volume of the water, because the cone is filled with water to the brim, is completely filled with water. So it's filled with water to the brim. So when a spear is lowered into the water, the volume of the water, when the spear is completely lowered into the water, the volume of the water that overflows will be equal to the volume of the spear. Okay, a spear is lowered into the water and its size. What is the size of the spear? Its size is such that the size of the spear is such that when it touches the sides of the cone, it is just immersed. It's just immersed, meaning the top of the spear just touches the top of the water. It is just immersed. I'll show you with the diagram. It's just immersed. What fraction of water overflows? What fraction of water overflows? So fraction of, don't write this, fraction of water that overflows, fraction of water that overflows will be the what is the volume of the water that overflows? Volume of the spear by the total volume. Okay, let me write that first. One minute, children. Let me write it still small so that I'll have more space. Here. Fraction of water. Listen carefully. Fraction of water that overflows. Is equal to volume of water that overflows. Volume of water, fraction of water that overflows is the volume of the water that overflows by the total volume of water. By total volume of water. This is how you find the fraction. The fraction of water that overflows. Like 1/4 of the water overflows or 2/3 of the water overflows. Fraction of the water that overflows is equal to the volume of the water that overflows by the total volume of the water. The fraction of water. See, if you are asked to find the fraction of boys in the class, what is the fraction of boys in the class? So it will be number of boys by the total number of students in the class. Fraction of boys in the class or fraction of girls in the class, whatever, is equal to, supposing you're finding for boys, it will be number of boys divided by the total number of students in the class. Similarly, here the fraction of water that overflows will be volume of water that overflows divided by the total volume of water. And now what's the volume of the water that overflows? It's exactly the volume of the sphere. Whatever is the volume of the sphere, that volume of water would have overflown. And what's the total volume of water? It's the volume of the cone. Whatever is the volume of the cone, because the volume of the water is the volume of the cone because the cone is completely filled with water. Water that overflows is whatever is the volume of the sphere. The sphere has taken some space inside the cone. So proportionately, some water overflows. Overflows water is volume of the sphere. Total volume of water, volume of cone. So this is what you have to find. You have to find the volume of the sphere by the volume of the cone. Now for the sphere, what do you need? You need the radius. And for the cone, radius and height. That's how you understand what to work. See, how do we know what should be the next step? Analyze this. Analyze this. Volume of the sphere. You know the formula 4 by 3 pi r cube. So you need the value for r. Children, are you listening? Am I clear?
Yes, ma'am.
Class, use the emoji.
ma'am.
Raise your hand. Thirunesh, Sudarshan, Shriya, Manasa, Shivani, Parkavi, Muttuvel, Srinivasan, Nivedita, Lakshita, Akshay, Balaharish and Shakti. Very good. All right, children. All right. So for the sphere, we need the radius. We need to find the radius of the sphere. That's not given. Radius of the sphere is not given. It's nowhere in the question. But for the cone, we have both the values. We know the radius of the cone, 12 centimeters. We know the height of the cone, 16 centimeters. So cone, we have everything. Radius, we know the height also. So you can find the volume of the cone. But for the sphere, we need R. So that's all. You should just find the value of R. Once you find R, you can find the fraction of the water that overflows. Is this much understood, children?
Yes, ma'am.
Please say yes or no. Okay. Class?
Yes, ma'am.
Yes, ma'am.
All right. All right, children. Have you copied the question? I need to clear the slide.
Yes, ma'am.
All of you?
Yes, ma'am.
Okay. I'm just about to clear the slide. Okay, I'm scared somebody will say you haven't. So let me include them. I can't include any of the slide now. Okay. So this is how we represent the information. Cone. Okay, so the sphere is just immersed, meaning it should touch the top of the water. The sphere is just, see, that sphere touches the sides of the cone. The sphere touches the sides of the cone, so it will be like this. And it is just immersed, meaning it will touch the sphere will touch the top of the water. The top surface of the water, it will touch like this. Children, it's not a triangle and a circle. Please understand, it's a cone with a sphere inside it. The triangular thing represents the cone and the circular thing represents a sphere. Okay, so this will be the perpendicular height of the sphere. Oh, sorry, cone. Perpendicular height of the cone. why have we drawn the sphere like this? The sphere is just immersed. The sphere touches. When the sphere touches the sides of the cone, it is just immersed. When the sphere, it's given in the question, when the sphere touches the sides of the cone, so it touches the sides, you can see it touches the sides. When it touches the sides of the cone, it is just immersed, meaning it will touch the, the level of the water on the top. It's just immersed. Okay. Now, what have we given children? I forgot. What is the radius of the cone, children?
12 centimeters.
Okay, thank you. 12 centimeters. And what's the height of the cone? It's given 16. Very good. Okay, 16 centimeters. Okay. Now, if supposing this is the center of the sphere, if supposing this is the center of the sphere, you can see that this one acts as a tangent to the circle. This portion. This one acts as a tangent to the circle. This looks like the point of contact. This is the center of the sphere. So when you join the center of the sphere to this point of contact, you know that the radius and the tangent at the point of contact are perpendicular to each other. So 90 degrees here. Similarly, this line acts as a tangent. This one, point of contact. Center, when you join the center to the point of contact, radius. This is the radius. You can see this is the radius. This is the radius. Radius of the sphere. Radius of the sphere. This one acts as a tangent, perpendicular. And this one is perpendicular already because it's the height of the cone. The perpendicular height of the cone. This is 90, perpendicular height of the cone. This one is 90, perpendicular height of the cone. Perpendicular height of the cone, so 90 degrees. So here, this is the center of the sphere. This is the center of the sphere. This is the radius of the sphere. These line segments act as tangents. So radius and tangent at the point of contact perpendicular to each other. So we have 90 degrees here. Now using 12 and 16, what can we find? Can we find the slant height?
Slant height.
Yeah, the radius is 12 centimeters. The perpendicular height is 16 centimeters. So the slant height, L square is equal to H square plus R square. So we have L square is equal to 16 square plus 12 square. 256 plus 144, 400. So L is equal to square root of 400, 20 centimeters. The slant height is 20 centimeters. The slant height, this full thing, children, this full thing, the slant height is 20 centimeters. Is this much understood?
Yes, ma'am.
Yes.
Yes, ma'am.
All right. So the slant height is 20 centimeters. Now, this acts as an external point of the circle. This one. So if this is 12, this is also 12, right?
Yes,
So
ma'am.
how much is the remaining here? How much is the remaining here?
8 centimeters.
It does not look proportional, my diagram. 12 centimeters looks very small. 8 centimeters looks longer than 12, but ignore it. That's meaning I cannot show it very accurately, but these are the values. If this is 12 centimeters, this is also 12 centimeters. Like this is the external point. Tangents from the external point of the circle are equal. Okay, so if this is 12, this is 12, but the whole thing is 20. So 20 minus 12, this remaining portion will be 8. See, from here to here, the slant height is 20. But this portion is 12. This portion is 12. This one is 12. So this one will be 20 minus 12, 8 centimeters. Now we need to find the value of R. You can use trigonometry. You can use similar triangles. See, first what we have done is using 12 and 16, using the radius of the cone and the height of the cone, we found the slant height of the cone. That is one thing. And then we use the property of tangents from an external point of the circle. They're equal. So 12, 12, so the balance is 8. So we did whatever numerical work was possible, we have done that. Okay, now let me just mark. Okay, I'll call this A, B, C, D, O. This point is E, children. F. Right, now let's try to use similar triangles. Prove that triangle. See here. Okay, I'm talking about the triangles. See, we have two sides of the figure. We have marked everything on this side. So I'm using the triangles on this side, children. See here. This figure, you have two sides. See, I have not marked 12 here. I have not marked 12 here, right? We have this side also in the figure. Since I've marked everything on this side, I'll take two triangles on this side. You can take this side of the figure or this side of the figure. Not that you should mark here only. You can even mark on this side of the figure. Since I have marked here, I'm going to take two triangles from here. Okay, so we need to prove that triangle. I'm not writing the order correctly. I'm just naming the triangles AOE and ADB. This is not the correct order, but I'm just naming the triangles. You need to prove that AOE triangle and ADB triangle. Look out for the triangles AOE and ADB. You need to prove that these two triangles are similar to each other. Is AOE a right triangle? Is AOE?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
It is a right triangle. Is ADB a right triangle? ADB?
Yes, ma'am.
Yes, ma'am.
Yeah, so there itself we have one information. Both are right triangles. Okay, so one pair of equal angles we already have. Now, which is the angle common to the two triangles? There is one angle which is common. AOE triangle, ADB triangle. Which
No,
angle
ma'am.
is common?
EAO.
Angle A, ma'am. Angle A.
EAO.
EAO or angle A.
Yes,
EAO is also BAD, correct?
yes, ma'am.
So there is one common angle and there is one right angle, meaning one pair of angles common, the other pair right angles. So the two triangles are similar by the AA similarity criterion. So take up the two triangles in triangle AOE and triangle ADB. Let me just number it. I'll just number it 1, 2, and 3. It's easy. Okay. Angle 1 is equal to angle 2, 90 degrees. Because, okay, I'm not writing the reason. 1 is because the radius is perpendicular to tangent. 2 is because of the perpendicular height. I already told you that. Then angle 3 is equal to angle 3 common. Now tell me the order. What is the order? Therefore, triangle. This is the common angle, right? Let me write one triangle. This is the common angle A. E is the right angle. O is the third angle. Is similar to which triangle? Sorry, is similar to triangle. Tell me the order. I've written the common angle first, the right angle, and then the third angle. Yeah, similar to triangle.
ADB, ma'am.
AB.
ADB, ma'am.
D or B first?
ABD, ma'am.
DB, ma'am.
DB, ma'am. DB, ma'am.
ADB, ma'am.
Correct. A, common angle. E is 90, D is 90. Third angle, third
D.
angle. Okay, very good. So the two triangles are similar by the AA similarity criterion. Now, we know that in two similar triangles, corresponding sides are proportional, which means AE by AD, See, this much we are doing to find the radius, children. That's all. First, we did some numerical work. Whatever we could do, we did that. And then we took up two triangles. We are proving that they are similar. Why all this? Because we want to find the value of R of the sphere. That's all. Once you find R, you can find the fraction of water that overflows. EO by DB is equal to AO by AB. Now fill the values. How much is AE? How much is AE?
8 centimeters.
8 centimeters.
8 centimeters.
AD?
16 centimeters.
16.
16 centimeter.
Yeah. EO?
R, ma'am.
Very
R.
good. R. EO is R, the radius of the sphere. Yeah. DB?
12
12
centimeters.
centimeters.
Yeah, this itself is enough. This itself is enough to find R. You don't have to write, so you don't have to write this at all. This itself is enough. You can find R from this. But if at all you have to write, what should you write for AO? How much is AO? What is AD?
And 12 centimeters.
AD. AD.
16.
16 centimeters.
Okay, so what is AO? What will be AO? A to O. A to O will be A to D, 16 minus DO, which is R. If you want to write, this is what it will be. AO. AO we don't know. So AO can be written as AD AD minus DO. Okay, let me write here. AD minus DO. This is AO. AO. AD. Look at the figure. AD minus OD. Okay, OD or DO. OD. OD or DO. 16 minus R. Because OD is the radius of the sphere. OD is the radius of the sphere. 16 minus R by what is AB? AB
20 centimeters.
20. So you can equate anything. You equate two things and find the value of R. That's all. Equate two things and two ratios and find the value of R. So that is your task. I'll do this one. 8 by 16 is equal to R by 12. 8 ones are 8 twos are. So on cross multiplying, you get R is equal to 12 by 2. So the radius of the sphere is 6 centimeters. Please write down, children. Please write. We haven't finished the answer. But write down so far.
Well, we can find by Pythagoras theorem also.
Yeah, we can find by Pythagoras theorem. We can find using trigonometry. Yes. We can find using Pythagoras theorem also. We can find using Pythagoras theorem. That is, you should take up only triangle AOE. Take up triangle AOE. Then apply Pythagoras theorem there. That's all. You can get it. In triangle AOE, OE is R, AO is what did we do? 16 minus R, and the other side is 8. So you can use Pythagoras theorem and find the value of R. Done, children?
Yes, ma'am.
Okay, now all of you find. I already wrote that earlier for you, no? Write down now. Fraction of water that overflows is equal to. Okay, so fraction of water that overflows is equal to volume of water that overflows divided by the total volume of water, which is equal to volume of sphere. I explained this already, by volume of cone, which is 4/3. There's no place. Read it. So I'm continuing here, which is 4/3 pi r cubed divided by 1/3 pi r square. What's the value of r? 12 square into h, 16. So 3 and 3 will get cancelled. Pi and pi gets cancelled. The value of r is 6. 6 into 6 into 6 divided by, oh, there's 4 here. No, I forgot. 4 into 6 into 6 into 6 divided by 12 into 12 into 16. So 6 ones are 6 twos are 6 ones are 6 twos are 2 and 2, and this 4 will get cancelled. And then what is remaining? 6/16. If I'm not wrong, 6/16, which is 3/8. 3/8 of the water overflows. 3/8. The fraction of water that overflows is 3/8. Is it fine, children? Is it okay, children?
Yes, ma'am.
All right. Okay. We'll do this one and then the examples in this chapter. So here in the given figure, we are continuing with circles, children. We did these in the last class. These in the last class. We did in the last class. Here in the given figure, xy and x dash y dash. Xy and x dash y dash are two parallel tangents to a circle. So xy is a tangent at P. Xy is a tangent at P. X dash y dash is a tangent at Q. I'm reading from the figure. There are two parallel tangents. Not only they are tangents, they are parallel tangents. Okay, that means POQ should be the diameter. If two tangents are parallel to each other, then if you join their points of contact, P and Q, that will pass through O and it will be the diameter to the circle. If two tangents are parallel to each other, then the line segment joining their points of contact will be the diameter to the circle. So it's given that xy is a tangent, x dash y dash is a tangent, P point of contact, Q point of contact. If you join, see now you will say it's given here, but that's also a property. So when you join the points of contact P and Q, when you join PQ, it will pass through O and PQ will be the diameter to the circle. When you join P to Q, the point of contacts, sorry, the points of contact. When you join, it will pass through O and PQ will be the diameter to the circle. Conversely, circle, and supposing I say that this is the diameter, I say AB is the diameter. So then the tangent through A and the tangent through B will be parallel to each other. Converse. Circle. Diameter AB, tangent through A. Okay, tangent through A. Tangent, children, please understand it's a tangent. Tangent through B. Okay. Since we know that AB is the diameter the tangent through A and the tangent through B will be parallel to each other, will be parallel to each other. Because this is 90 degrees, this is the tangent, and this is the diameter. That means this is the radius. So radius tangent to the point of contact 90. Here also radius tangent to the point of contact 90. And you can see co-interior angles are supplementary. Co-interior angles are supplementary, 90 plus 90, 180. So the lines are parallel to each other. See here, like this. This is 90, this is 90. Co-interior angles are supplementary. So that means these two lines are parallel to each other. Okay. So when two tangents are parallel to each other, the line segment joining their points of contact will be the tangent to the circle. Oh, sorry, will be the diameter to the circle. Let me repeat it. When two tangents are parallel to each other, the line segment joining their points of contact will be the diameter to the circle. Here what I said is, if you know, or the tangents drawn at the ends of the diameter, the tangents drawn at the ends of a diameter, so this is the diameter, we have tangents drawn at the ends of the diameter, will be parallel to each other. Will be parallel to each other. If you know this is the diameter, these two tangents will be parallel to each other. If these two tangents are parallel to each other, then this is the diameter. If this is the diameter, then the tangents are parallel to each other. If the tangents are parallel to each other, then this one will be the diameter. Okay, there are two parallel tangents, and there's another tangent AB with the point of contact C. There's another tangent. See, this is another tangent with point of contact C. XY is a tangent with point of contact P. X dash, Y dash is a tangent with the point of contact Q. There is another tangent AB with the point of contact C. So totally they have described three tangents here. And the tangent AB intersects XY at A. You can see it there, and X dash, Y dash at B. Prove that angle AOB is 90 degrees. Prove that AOB is 90 degrees. This one is 90. So what is given? XY is a tangent at P. X dash, Y dash is a tangent at Q. AB is a tangent at C. And we know that PQ is the diameter. Given all this, we need to prove that AOB is 90 degrees. So children, join OC, show that these two triangles are congruent to each other. These two triangles are congruent to each other. So when you prove that, join OC, prove that these two triangles are congruent to each other. These two triangles are congruent to each other. When you prove that these two triangles are congruent to each other, you will get the result angle 1 is equal to angle 2. And when these two are congruent to each other, you will get the result angle 3 is equal to angle 4. CPCTC. But we know that, so you will get the result angle 1 is equal to angle 2, CPCTC, congruency. Angle 3 is equal to angle 4, CPCTC. But since POQ is a straight line, because we know POQ is the diameter. We know that POQ is a diameter, it's a straight line. So we know that angle 1 plus angle 2 plus angle 3 plus angle 4 is 180. Is 180. Now instead of angle 1, you can say angle 2 plus this 2 as it is. plus this 3 as it is. Instead of angle 4, you can say angle 3 because you know that 3 is equal to 4. See, you need to prove that 2 plus 3. What is AOB? You need to prove that angle 2 plus angle 3 is 90 degrees. AOB means 2 plus 3. 2 plus 3. AOB. 2 plus 3 is 90. So get rid of 1 and 4. Take away 1 and 4. Instead of 1, you say 2. And instead of 4, you say 3. We need to prove that 2 plus 3 is 90. So you don't want 1 and 4. What is 1? It's 2. And what is 4? It's 3. So you get twice of angle 2 plus twice of angle 3 is 180. 2 common. Angle 2 plus angle 3 is 180. So angle 2 plus angle 3 is equal to 180 by 2, 90 degrees. Which means angle AOB, 2 plus 3 is AOB is equal to 90 degrees. Please write down, children. What I've also done here is that I've explained the congruency in detail. That's why it looks lengthy. It looks like a lengthy proof. So this is just that these two triangles are congruent, no? So that is explained in detail. And see here, 1 is equal to 2 CPCTC. Then again, the other two triangles congruent is explained. Then this 3 is equal to 4. 3 is equal to 4. See this CPCTC. Then 1 plus 2 plus 3 plus 4. You can see it here. 1 plus 2 plus 3 plus 4 is 180. Then what we just understood. Children, why don't you take a screenshot and complete this, children? I want to complete the examples in this chapter also. I think you can take a screenshot and complete this. Take a picture, I've explained it. All right. This is understood, children?
Yes.
Any questions?
No, ma'am.
Okay, thank you. So here, prove that in these are examples from the same chapter, circles. Prove that in two concentric circles, the chord of the larger circle which touches the smaller circle. Touches the smaller circle meaning it's a tangent to the smaller circle. If a line or a line segment touches a circle, it's a tangent to the circle. If a line or a line segment touches the circle, then it's a tangent to the circle. Prove that in two concentric circles. So let us draw two circles which are concentric. Prove that in two concentric circles. In two concentric circles, the chord of the larger circle which touches the smaller circle. So it should be a chord to the larger circle. It should be a chord to the larger circle and it should touch the smaller circle like this. So see, this line segment is a chord to the big circle and it's a tangent to the inner circle at this point. This line segment is a chord to the outer circle. That's what they asked it to do, asked us to take. The chord of the larger circle. The chord of the larger circle. So you can see that this is a chord to the larger or the outer circle, which touches the smaller circle. So see here, the chord touches a smaller circle at this point, which touches a smaller circle, is bisected at the point of contact. So that means you should prove that this one is the midpoint of the chord. If you call the chord AB and P is the point where it touches the inner circle, you must prove that AB is bisected at P, the point of contact P. That means you must prove that AP is equal to BP. You must prove that AP is equal to BP. You can see AB is a chord to the outer circle. AB is a tangent to the inner circle at P. AB is not a chord to the small circle. AB is not a chord to the small circle. It's a chord to the big circle. It's a tangent to the smaller circle at P. We should prove that P is the midpoint of AB. That is AP is equal to BP. All right. So let's mark the center. This is the center. We'll join OP. We'll join OP. Join OP. And we know that since OP is the radius and AB is the tangent, this is 90 degrees. This is 90. Because OP is the radius and AB is the tangent. Radius tangent at the point of contact perpendicular to each other. Now, you can do it in two ways. One is you can join AO, you can join BO. Prove that these two triangles are congruent to each other, so you will get AP is equal to BP. So tell me the information to prove that the triangles are congruent to each other. APO and BPO. Yeah. APO, BPO, how are they congruent?
AO equal to BO, ma'am.
Okay, AO is equal to BO.
Angle OPA equal to angle OPB, ma'am.
Correct.
And then OP equal
AP
to
equals to
What's that? AP equals BP, yeah? That's what we have to prove. You cannot write that now.
OP equals OP, ma'am.
OP equal to OP, ma'am.
OP is equal to OP common side. OP is equal to OP common side. So what rule it makes?
RH.
RHS, right? RHS. RHS rule congruent. So AP is equal to BP, CP, CTC. You can do it like this. You can prove that the triangle APO and the triangle BPO are congruent to each other by RHS rule. Then CPCTC, AP is equal to BP. Or without using congruency, you can directly so you know that this is 90 because radius tangent perpendicular to each other is 90. And then again in 9th standard we have learned a theorem which says that the perpendicular, if the perpendicular from the center to the chord bisects the chord. We have learned that.
Yes, ma'am.
Yeah, a perpendicular from the center to the chord bisects the chord. So AB is a chord. AB is a chord to the outer circle, and OP is perpendicular to the chord AB. So the perpendicular OP from the center to the chord AB bisects the chord. So AP is equal to BP. Or you can prove, if you don't want to use this theorem, then you have to join OA, join OB and prove that the triangles are congruent and then say AP is equal to BP, CP, CTC. Otherwise, you can say the perpendicular from the center to the chord bisects the chord. So OP is the perpendicular from the center to the chord. So it bisects the chord. So AP is equal to BP. Please take a screenshot. Done, children?
Yes, ma'am.
Okay, so you can see that why do we say OP is perpendicular to AB?
Radius is
Perpendicular to the tangent at the point of contact. Because see, AB plays two roles. The line segment AB, this line segment AB, it plays two roles. It is a tangent to the inner circle and it's a chord to the outer circle. So you should use it accordingly. AB plays two roles. It is a tangent to the inner circle. It's a chord to the outer circle. So when you take it as a tangent to the inner circle, OP is perpendicular to AB. OP is perpendicular to AB, radius perpendicular to tangent. Now the tangent role is over. Now let us take the other role, chord. The perpendicular, now we know this is 90, no? So this is the perpendicular. The perpendicular from the center to the chord bisects the chord. The second role is chord, right? So the perpendicular from the center to the chord bisects the chord. So AP is equal to BP. All right. So here the figure is given to us, children. The figure is given to us. I've just numbered it 1 and 2 here. I've just numbered it 1 and 2. We need to prove that PTQ, I've called PTQ as angle 1. PTQ is twice OPQ. It's twice OPQ. See here, OPQ, this one, OPQ, this angle. In other words, we'll have this is angle 1. PTQ is angle 1 is equal to twice of angle 2. That's what we have to prove. That's what we'll have to prove. Okay. So to prove this result, children, just take up this triangle. Look at this triangle. Take up this triangle. Take up this triangle. Use angle sum property. See here. In triangle, please see here. In triangle TPQ. TPQ in that triangle. Use angle sum property. Angle 1 plus angle TPQ plus angle TQP is equal to 180. The sum of the three angles in this triangle is equal to 180. Angle 1, this angle TPQ and this angle TQP is 180. Now we know that PT, this PT is equal to PQ, PT is equal to QT because they're tangents from the same point, T to the circle. So they're equal. TP is equal to TQ. TP is equal to TQ. That means this angle is equal to this angle. These two angles are equal. So if these two angles are equal, instead of this TQP, you can also write, see here, first the sum of the three angles is 180. Then since TP is equal to TQ, this angle is equal to this angle. So instead of this angle, you can write TPQ itself. So see here, TPQ plus TP. Instead of this also, you can say TPQ. They're equal. Otherwise, you can number it, children. Supposing you have any difficult to understand. See, you can just number this angle 3, angle 5. So I'm saying angle 1 plus angle 3 plus angle 5 is 180. But angle 3 and 5, they're equal. Why? Because TP is equal to TQ. So if those two angles are equal, angle 3 is equal to angle 5. So angle 1 plus angle 3, instead of 5, say 3 itself. Is equal to 180. That's what I've written. Let me come back. We use the triangle TPQ. Angle some property. Angle 1 plus this angle is equal to 180. But since these two sides are equal, this angle is equal to this angle. So instead of angle TQP, we'll say TPQ because they're equal, TPQ. So that's what you see here. Angle 1 TPQ is 180. Angle 1 plus twice TPQ is 180. But what is angle TPQ? TPQ is, this whole thing is 90. This whole thing is 90. This whole angle is 90. 90 minus angle 2 is TPQ. See here? This full angle is 90 because radius tangent perpendicular to each other. This is the radius. This is the tangent perpendicular. This is the radius. This is the tangent. They're perpendicular. And 2 is here. 2 is here. So what is 90 degrees minus angle 2? It is this angle. 90 degrees. This whole thing is 90 because radius tangent perpendicular. OP is the radius. This is a tangent. They're perpendicular to each other. So 90 degrees minus angle 2 is this angle TPQ. TPQ is 90 minus 2. I've already worked that first. TPQ is 90 minus 2. Because the full thing is 90 and this one alone is 2. So 90 minus 2 is TPQ. You can see here. TPQ is 90 minus angle 2. TPQ. Okay, so substitute that here. And that's it. On working this, you will get the result. Angle 1 is twice angle 2. So it's just by using angle sum property, children. That's all. It's just by using angle sum property in this triangle. Since these two sides are equal, this angle is equal to this angle. These two angles are equal. Then for this angle, you must say it is 90 degrees, this full angle, 90 degrees, this full angle minus angle 2. Tell me, children. So simply by using the triangle TPQ and angle sum property, we get the result. All right.
Yes.
Yes, ma'am.
Okay. Just a minute, children. Okay, so this one, this PTQ, this one is PTQ. See, it's given TP and TQ are tangents and center O. The figure is given, children. The figure will be given to you. Okay, so prove that, yeah. So PTQ I marked angle 1 and OPQ, this one is angle 2. So use angle sum property in triangle TPQ. Tell me, angle 1 plus angle
TPQ
plus angle
TQP.
TQP.
TQ is equal to 180. Then angle 1 plus this side is equal to this side. So this angle is equal to this angle. Now since angle 2 is here,
Angle TPQ.
yeah, we'll retain this angle because angle 2, this angle is close to angle 2. So we'll retain this angle. TPQ will write TPQ. Instead of TQP,
Again TPQ.
TPQ. Because both are equal, is equal to 180. So angle 1 plus twice of angle TPQ is equal to 180. Angle 1 plus twice of. So now TPQ can be written as TPQ. The whole angle is 90.
minus OPQ.
From here to here is 90. This full angle is 90. 90 minus angle 2 is TPQ. 90 minus angle 2 is TPQ. Is equal to 180. When you work this, you will get angle 1 is equal to twice angle 2. When you work this, you will get angle 1 is equal to twice angle 2. That's what we have to prove. Children, I'll just explain this and we'll wind up the session for today. Okay, so okay, so in this figure you can see a circle with center O. You can see the tangents TP and TQ, and you know that TP is equal to TQ. The length of the chord PQ is 8 centimeters. The length of the chord PQ is 8 centimeters. This question is mostly asked, so I can say it's an important question. This question is important. Circle with center O, TP, TQ, tangents from T. PQ, the length of the chord PQ is 8 centimeters. Radius 5 centimeters. With this information, we need to find the length of the tangent segment TP. What is the length of TP is what we have to find. How much is TP? How much is TP? Chord PQ is 8 centimeters. Radius is 5 centimeters. You should find TP. How much is TP? So children, for this one, what you can do is, again, you can use Pythagoras theorem. You can use similar triangles. I'll tell you using similar triangles. You should just try to, include the line segments whose lengths we know. See, we know some 8 centimeters, 5 centimeters, and then maybe we can find the length of some line segments. So why similar triangles? Because similar triangles, in the proportion you have 6 line segments. So by substituting the values for whatever you know, you can find the unknown TP. So you should take 2 relevant triangles from which proportion you can find TP. If I zoom in, I cannot annotate. So let me do this. So children, we have to take up, I'm explaining from behind. Listen, prove that this triangle, this triangle is similar to the whole triangle, This one small triangle, no? Prove that this one small triangle, that is prove that triangle ORP. My order is not correct. I'm just naming the triangle. ORP is similar to TPO. Simply prove that these two triangles are similar. Write the proportion. You will get the answer. That's all. Show you again. Show that this small triangle is similar to this whole triangle. That is, show that ORP and OPT are similar to each other. But OPT is a right triangle, children. You can see there, OPT is a right triangle. That means ORP also should be a right triangle. If they have to be similar. Because in similar triangles, corresponding angles are equal. Sides are proportional. So if there is 190 degrees in one triangle, in the other triangle also there should be 190 degrees. Because in two similar triangles, corresponding angles are equal. So if there is 90 degrees in one triangle, there should be 90 degrees in the other triangle, which is similar. Listen carefully. So I'm saying OPT is a right triangle, OPT, because this is 90, radius and tangent perpendicular to each other. This is the radius, this is a tangent, they are perpendicular. OPT is 90. That means you should prove that ORP is also 90. ORP is 90. Okay, so how to prove ORP is 90 is easy. We'll come to that later. Now, when you take up the triangles, so let me start from here. See here, children. See the triangle OPT, the big triangle OPT, and the small triangle OPR. Okay, OPT is 90. Children, please follow. OPT is 90 because radius tangent perpendicular. ORP is 90. I'll tell you how. This one is 90. We can prove that this is 90. I'll tell you how later. Okay. We can prove that this is 90. It's very simple. So 90 degrees, both are right triangles. And then this is the common angle. This is the common angle. In both the triangles, you have this one. In the small triangle also, you have this angle. In the big triangle also, you have the same angle. So this is the common angle. For the big triangle, it is POT. For the small triangle, it is ROP. But both are the same angles. So the two triangles are similar. See, so the two triangles are similar. This is the common angle. O is the common angle. P and R are right angles. P is 90 degrees, R is 90 degrees. I'm pausing so that you understand. O is the common angle and P and R are right angles. So that order I have followed. I've written the common angle vertex first and then the right angle vertex. Then the third angle. So the two triangles are similar. Then write the proportion, fill the values and get PT. That's all. Now coming to how to prove that this is now coming to how to prove that this is 90. That's also simple for you. You know how to show that these two triangles are congruent to each other. Once they are congruent, angle 3 is equal to angle 4 CPCTC. But 3 plus 4 is 180 because they are on a straight line. So angle 3 will be 90, which means this is 90. This triangle, see here, this triangle, and this triangle, you can show are congruent to each other. Once they are congruent, CPCTC, you will get angle 3 is equal to angle 4. If angle 3 is equal to angle 4, that means angle 3 is 90 because how can 3 and 4 be equal? If they're equal, angle 3 is equal to angle 4. But you know that angle 3 plus 4 is equal to 180. But they're equal. That means 3 is 90. 3 is equal to 4. Angle 3 is equal to angle 4. That means 3 should be 90 degrees. Because you know the steps 3 plus 4 is equal to 180. Angle 3 plus angle 3 is 180. Twice of angle 3 is 180. Angle 3 is 90 degrees. So if this is 90, if this is 90, this is also 90. That's how you prove that this is a right triangle. We have to get 90 degrees here, no? So we got it. If this 90, see, this is 90, this is 90, then everywhere it's 90. So children, step 1, show that this triangle. So you know that you'll have to prove that this angle is 90 degrees. Yeah. So show that this triangle is congruent to this triangle. So you'll get 3 is equal to 4. If 3 is equal to 4, but 3 plus 4 is equal to 180 linear pair. So you'll get 3 plus 3 is equal to 180. So angle 3 is equal to 90 degrees. Angle 3 is 90 degrees. So this way you prove that this one is 9. The small triangle is a right triangle. The small triangle is a right triangle. This one is 90 we got. Now the big triangle is a right triangle because radius and tangent at the point of contact perpendicular to each other. Now take up the two triangles, the two right triangles. Show that they are similar. Write the proportion. In similar triangles, corresponding angles are proportional. And fill the values. So children, here you need to use Pythagoras theorem and find OR. OR will be 3 centimeters because PQ is 8. That means PR is 4, RQ is 4. PR is 4, RQ is 4. Because PQ is 8 centimeters. PR and RQ, 4, 4. Again, CP, PR is equal to RQ. So you can find OR using Pythagoras theorem. Because this is 5 and this one will be 4. This part, this alone will be 4. This is 4, this is 5. So Pythagoras theorem, this is 3. This is 3. That's all. Write the proportion, fill the values, and you find that PT is 20 by 3 centimeters. Is that fine, children?
Yes.
Yes,
ma'am.
Yeah, please take a screenshot and complete this. So you'll have to complete 3 answers. All right, children. I hope you took a screenshot of this one. All right, children, thank you so much. That's it for today's session. Thank you. Good night.
Thank you, ma'am.
thank
Thank
you,
you.
ma'am.
Thank you, children. Good night.